Hello. So I'm going to be talking about our solution for traffic control, and first maybe we should start with introducing the domain. So the problem of traffic control is known to all of us, I think, at least as pedestrians, in our role as pedestrians, but also some of us, the lucky few of us have driving licenses, so they can attest to that side. And it's kind of like a quirky topic, but also if you think about it economically, there are like literally billions of dollars lost every year to traffic. So there are a lot of efficiencies to unlock there for a good solution. And maybe we should start with how it's actually done in practice. So the first traffic lights, they are 150 years old for now, and they've been operated manually. And the solution that is actually used by most of the people now is either just a system that runs on sort of factory settings of each traffic light, but has some light synchronization to enable the so-called green wave, which is where if you're driving at a major route, you have a higher chance than not to hit a streak of lights. So it's unlikely that well, it is likely that you will hit just one green traffic light, but it is also more likely than would be random that you will be just like driving all the way through with no stop. And also some PID control, which has the benefit of being like adaptive in a way, because it takes current conditions as input after all, but has the drawback of not being like adaptive in the long term. So if we control something with PID control, we can adjust for make adjustments for changes that happen on the scale of like second to second, maybe minute to minute, but it's very unlikely that we will be able to say recognize that a traffic jam is incoming because there's, I don't know, there's a political visit in town and we have to adjust for blocked routes or something like this.
So a couple of years ago, RL approaches started to emerge for this problem. And if you think about it, RL seems like a very good idea because the problem in general is hard. But if you were to control a given traffic light, it's very hard to say which exactly is the correct action to make. Whereas if you think about it in terms of rewards, it's actually quite convenient because you can take a look at, let's say, the amount of vehicles passing through an intersection or the time they have to wait at a traffic light. And that's a perfect example of a reward that you could use in an RL algorithm. So yes, these approaches, as soon as they started emerging, obviously you started to need a simulator. You can't run it in a real world, but you need to explore and so on. So simulators started to emerge as well. Some of them initially very simple. You could even say quite simplistic and unrealistic, but some of them later on quite complex, quite powerful as well. But long story short, regarding the previous approaches to RL in this problem, we didn't really like them that much because of the following problems. These models that people have been working on have been were dedicated in given training to a given kind of area of the road network. So for example, you took an area of a city, specific traffic lights, you construct a model, then you train for it, but you cannot generalize because a given agent, a given some part of the parameters dedicated to a given light, the agent learns that certain roads mean something, that, for example, incoming roads are important, whereas outgoing maybe not so much. So you cannot generalize it. It's stuck. You are stuck with this scenario. But of course, in the end, you don't want to control, let's say, one simple traffic light. You want to take, let's say, a big piece of the city. And what happens then is basically it becomes a big mess with a lot of things going on, with the rewards in the algorithms being potentially very delayed. Because if you, for example, take an approach to reward modeling where you, after the vehicle leaves the area you control, you assign the reward then you can obviously think of a case where some action very early on was crucial, and yet the rewards happens much later. Um, And yeah, so one thing is the network, like the structure of the roads, and another is the phases of the traffic lights. If you think about it, for some intersections you might have just two roads incoming. For some of them you might have 10, and there's a different configuration of the traffic lights that you can control. So with these approaches, where the model didn't have any kind of priors in the architecture, it simply learned that, let's say, action 0 means that certain lanes are moving. You just cannot generalize it to different networks. And also the thing is, like I said, the problem is quite, if you take a look at the simulations, if you take a bunch of roads, a bunch of traffic lights, it becomes very complex, whereas you are just stuck to your scenario, your traffic that you have modeled. So basically there's very limited data that you can use for training. Now, if we are talking about RL, you obviously need an environment. So let's quickly take a look at what's available. Some of the simulations are quite simple, but Sumo is a perfect example of something that is quite realistic. It has a lot of things going on under the hood. It models a lot of stuff. It's got different kind of objects like edges, lanes, internal edges, junctions. It handles entities like passenger cars, trains, pedestrians, and so on. So a lot of it's quite complex. It's quite hard to work with sometimes. But long story short, what matters is we think it can model the real world quite reliably. It's plausible, so it's a good substitute for the real world. One of the important things, which is not always the case with the simulators, is that in Sumo you have access to pretty much anything that is going on under the hood. Like, for example, you can access every single vehicle that is modeled. You have access to its speed, to any internal parameters and state. So basically, you can shape your rewards, you can shape your state functions however you want. Yeah, that's just a demonstration of what can it do. It's got even a nice UI where you can take a look at the performance of the agent. It models stuff like even crashes of the cars, forced braking, stuff like that. So yeah, like I said, it's quite plausible. It's a good environment to train our agent in. And now in Sumo, obviously, in the end, we are interested in traffic lights. We want to control them. So let's take a look at what state you have in a traffic light and how you control it. So if you take a look at the image, you've got on the right, there's an intersection. And for such an example, you are controlling the whole thing at the same time. The lines that you can see, the red and green lines, is what is called connections. And basically, each such connection connects one incoming lane with an outgoing lane. There's a concept of phases. A phase in a given intersection is a configuration, very specific configuration of every light within an intersection, which tells you whether one connection, you can drive through a connection or not. So on the left, there's four phases available for an intersection. And there's a bunch of letters, there's R's, there's G's. And as you can imagine, R is red light. G is green, there are yellow and some other states. But in the end, what's roughly happening is for each of the lines that you can see on the right, for a phase, there's going to be just one specific light. You either can go through or not. And at the bottom, you can see a different phase selected where the colors basically changed. So that's what we'll be using in our model. We'll be modeling on the level of these connections, these lines. We will be constructing a graph. The model will be graph-based. And in our case, even though if you take a look at the specification of the entire simulation model in Sumo, it's very complex with a lot of things going on. But in the end, what we found is we can simplify it for our purposes, for our problem. We can simplify it to, obviously, we want to create as simple graph as possible to lower the dimensionality of the problem. And what we found is we can model it while handling every case we want to handle. We can model it with just two types of nodes in the graph. One node is going to be a lane. and one node is a connection. So these lines on the intersection, and there are relations between them. One thing to keep in mind, you can probably guess that these nodes have a state. They have attributes as well. So for example, for a lane, there's going to be a length of the lane, width, maybe how many sibling lanes there are, and so on. But also state during the simulation, which is going to be, let's say, a number of vehicles on a lane, their average speed, something like that. You can come up with any state function you want. But that's the graph that we are working with. And in our model, using such a graph and some let's say clever tricks, we will achieve our goal of generalizing across the scenarios. So first of all, we will be modeling every single node in the network. Previous approaches mostly considered traffic lights themselves. But if you think about it, that's a downstream problem, let's say. But initially, what you are interested in is basically modeling the traffic condition in the entire network. So what we'll be doing is constructing some kind of state, some kind of embedding of the state for each node in our graph. And as we'll describe shortly, our architecture will allow the model to generalize across arbitrary network road topologies. As such, it will allow us to train initially on very simple networks and then gradually start working on harder and harder, eventually coming to real-world scenarios that we wanted to model initially with a lot of things learned already.
Okay, so let me just take a minute to convince you maybe that our model indeed can, how it is graph-based and how we can modify this graph, which is the most important thing. So basically, we embed both connections and lanes as hidden states. And these hidden states pass through a number of self-attention layers. And these self-attentions are graph-based, which means that they are like the equivalent to a Hadamard product of the normal full self-attention and our graph. And the way this is done, this is one feature. And another feature is that we also add relation embeddings. So when the attention scores are computed, they are not computed by like query times key, where key is like only they are not computed for keys that only correspond to a given node. They are computed to keys that correspond to a given edge between nodes. So we have to take a little bit more space to store these keys and values. But on the flip side, we can adapt to the particular type of connection, particular type of edge between a node, and the node, the edge type is embedded itself. We add the embedding to the hidden state of the target node of an edge, and then we just pass them through queries, keys, and values, heads, and use standard multi-head attention. So in complexity terms, we're only modifying the complexity of usual self-attention by multi-head attention by a linear factor of E, where E is like max connectivity of a single node in our graph. So, and for these graphs, it's going to be very small. It's like 7 tops, like 8 maybe, but. And yeah, and maybe also how we output very quickly. We basically use a DDQN algorithm, which means that we output Q values. And for each intersection, we output Q values over the set of possible phases on that intersection. So it was on an earlier slide, so possible combinations of values of each traffic light in an intersection. And the nice thing is that we analyze, we pass the entire state of the simulation, so maybe thousands of intersections, thousands of lanes and connections from by our main model, and then only during the inference we can like extract information for a particular intersection and use it to output an action. So this is very modular and it's very nice. You can define lots of the graph structures on road networks, and we will support them because in LoRa style. There's not much parameters you have to change. But yeah, you also need to train our model. And for that, maybe talk about scenario generation. How do we do that?
So initially we started, we considered generating only synthetic scenarios, but we thought that maybe one could argue that they are not representative of the real world. So what we ended up doing is actually, it turns out that on OpenStreetMap, you are free to download basically any information about maps in cities, including the structure of the roads. So what we do is basically we download the data from OpenStreetMap. Using some already provided low-level tools in Sumo, we are able to parse it quite nicely. We convert it to the road network that is understood by Sumo, and we generate some synthetic traffic. So these are the examples of the networks that we can come up with. What we do is basically from all the cities in the world, we sample some cities, we sample the area that we want to consider, and we construct networks like this. And we define a curriculum. You can, well, imagine anything you want here, but what we do is basically we start with very simple scenarios with, let's say, one traffic light, two roads, which is very simple, and we want the model to learn the simplest stuff, and we gradually introduce harder, bigger networks and a lot more traffic, eventually coming to real-world scenarios with lots of traffic lights. And now about the results. Comparison to other methods is very hard in this case, because usually in machine learning problems, if you consider, let's say, image classification, the problem is very standard, defined in the standard way. So you have some images which always have, let's say, 3 channels, and you output one label. Whereas here it's very different, because everybody uses different simulators, different ways of interacting with the environment, different constraints, different outputs. So there's basically an option of either changing the previous approaches to handle what we want to handle, changing them so much that you basically change them beyond recognition, or you decrease the effectiveness of our approach by introducing changes to adapt to the stuff people used. So, and also it's very compute intensive, so what we have is very preliminary results. There's a lot of more training to be done, but what we have is displayed here. That's a comparison to one of the old school, but still very good methods, which is a heuristic called max pressure. And you can see here that for small roads, what we achieve in our method is a perfect score of 0. Smaller value is better. And it still generalizes to larger roads. Still a lot of work is to be done here, a lot of training, because it doesn't always happen like this for larger networks, but it proves that such a specification of the training works. The model learns the simple stuff as we want it and generalizes to stuff not seen during training. So that's the state right now. Obviously, like I said, there's a lot more training and grid search and so on to be done still, and a lot of room for improvement, a lot of interesting avenues for research, because it's very, very flexible. You can introduce very nice things into the architecture. And maybe one thing, interesting exercise to be done is to, rather than shape your, let's say, state functions the way, however you want, maybe you could try to adapt it to the requirements of the real world right now, what's available, what you can get, and so that you can try to deploy it in real life. And this is it. Thank you.
Thank you. So we have time for a really short one question. If not, so do you also include pedestrian times?
No, one of the avenues for further research is maybe reducing the simplifications that we make in order to make the problem of less dimensions, basically. So currently we model passenger cars only.
Okay. So thank you once again.